everyone, my name is Dr. Priyanka Mehta. I'm working as Assistant Professor in Zoology Department, Hansraj College. Today we are going to talk about nerve impulse transmission. To begin with, let's first discuss the structure of neuron. Neuron is the specialized cell present in the nervous tissue. It has many parts. These extensions are known as dendrites, which receive the impulses. Then we have a central structure which is known as soma. This is also known as cyton and also called as cell body, which carries nucleus. This is our nucleus. The long tube-like structure is called as axon, where the nerve impulse propagates, and these are called as nerve endings. These structures are also called as, the swollen structures are also called as synaptic nerve. Now, if the axon carries a myelin sheath over it, that would be called as myelinated axon. As we can see here that the myelin sheath is present over the axon, so this kind of nerve fiber would be myelinated nerve fiber and this kind of axon would be myelinated axon. Now the gaps where the myelin sheath is absent, that is called as nodes of Ranvier. So this is the basic structure of neuron. Now we are going to talk about how the nerve impulse propagates. So the nerve impulse propagates in 3 steps. First is the maintenance of resting membrane potential. Second is generation of action potential. And third is propagation of action potential. So this structure represents the gap between 2 neurons, right? And this space can be called as synaptic cleft. Right? And the communication between 2 neurons, that would be called as synapse. Now synapse can be of 2 types. It could be electrical synapse or it could be chemical synapse. That is one thing. Now for the nerve impulse to propagate, 3 things happen. First is resting membrane potential, which is called as RMP, the value for which is minus 70 millivolt. Now this is maintained throughout when the nerve impulse is not propagating any signal. So how is this maintained? So let's assume this is extracellular fluid and this is our cytosol. And this is our extracellular fluid. Now what happens, the concentration of ions like sodium, chlorine and calcium is higher outside. The concentration is higher outside. And for the inside, the concentration of potassium is higher and some anions is higher. As a result of which, the inside is negatively charged and the outside is positively charged. And there is a difference in potential across the membrane and the membrane is said to be polarized. So at resting state, membrane is polarized. Why is it polarized? Because there is a charge difference. Charge difference across the membrane. How is the charge difference maintained? Sodium ions are higher outside, primarily sodium ions, and potassium ions are higher inside. Also, we have anions which are negatively charged present inside. We have some non-diffusible molecules also present inside which cannot diffuse outside. And we have calcium ions which are positively charged present outside. Chloride ion are present both inside and outside, but the concentration is higher on the outside. Now interestingly, what happens, we have more number of leaky channels present for potassium as compared to sodium. So let's talk about leaky channels. Leaky channels will allow the leakage of ions from the region of higher concentration to lower concentration, which means along the concentration gradient. So leaky channels are higher for potassium and lower for sodium, as a result of which more potassium moves outside because the concentration is higher this side, so obviously they move outside, and less sodium comes inside because we have less number of leaky channels for sodium. We can also say this in the other form, which means the membrane is more permeable for potassium and less permeable for sodium, as a result of which the more positive leaves the cytosol and less positive enters, therefore leaving the membrane, the inside of the membrane, to be more negative. So the one factor which was contributing for the inside to be negative was the charge difference, higher sodium outside, less sodium inside, higher potassium inside, less potassium outside, more anions inside which are negatively charged inside, and non-diffusible molecules inside. That was the one reason. Second reason is number of leaky channels, which are higher for potassium, which means more potassium is going out, which means more positive is going out, leaving the inside to be more negative, as compared to the leaky channels for sodium, which are lesser in number, so less sodium is coming in. The other third reason is the sodium potassium pump. Sodium potassium pump, or we can also call it as ATPase, which because it utilizes ATP. So what happens here, as you can see, this is sodium potassium pump. To break the dissipation of charges, to maintain the resting membrane potential, this is the third factor which contributes. What happens, the sodium potassium pumps, it makes sure that via this pump, via the expenditure of ATP, 3 sodium will move out and only 2 potassium will move in, which means more positive is going out and less positive is coming in, as a result of which again the inside is more negative and outside is more positive. So this is the third factor contributing in the difference in charges across the membrane. So this is how resting membrane potential is maintained. That is the first step of nerve impulse transmission. Now, this region is known as axon hillock, where the nerve impulses arrive. So dendrites will receive the impulses and all the impulses arrive first at axon hillock. If we have an excitatory impulse or potential, that would lead to the opening of voltage gated sodium channels. Very important point over here. It leads to the opening of voltage gated channels, as a result of which there is influx of sodium ions. So sodium ions will move in, making the inside positive, right? So there's a charge reversal again, that is known as depolarization. So in polarized state also there was charge difference across the membrane, but outside was positive and inside was negative. Now there's a charge reversal when the action potential has arrived, when the impulse has arrived. So there's a charge reversal. Now we say that the membrane is depolarized. There is rapid influx of sodium ions, making the inside more positive. That is what is happening during depolarization. Now for depolarization to occur, or for it to reach action potential, first the membrane has to reach threshold potential or threshold value. The threshold value is minus 55 millivolt. So at resting state, let's talk in terms of graph. At resting state, the membrane potential was minus 70 millivolts. Then for it to reach the action potential, it must first reach minus 55 millivolt. We start from here, we reach here. Once it has crossed the threshold value, the nerve impulse will fire and it will reach the maximum value, which is plus 40 millivolt. So this follows the all or none principle. If it has crossed the threshold value, it will fire, and in case it hasn't, no matter the strength of the impulse, it will not fire the action potential. Right, so this state is known as depolarization. This is what depolarization is. We say that the membrane is depolarized because there is a charge reversal. Now what happens? Interestingly, especially the voltage gated sodium channels, they have three states. One is closed. When are they closed? When the membrane is polarized. So when the membrane is polarized, the channels are closed. And here we are talking about voltage gated sodium channels. Right? So the channel was closed, there was no influx of sodium ions. Via voltage gated channels, leaky channels are open throughout. The next state is voltage gated sodium channels are open, so sodium can move in. This happens during depolarization. Right? And the third state is inactivated. When the channel gate is inactivated, this occurs during repolarization. This I will just explain. So during repolarization, voltage gated sodium channels are neither open nor closed, rather they are inactivated. So what happens next? There was influx of sodium ions, there was charge reversal, the inside became positive and it reached the peak, which is plus 40 millivolt. Now repolarization has to occur. So the voltage gated sodium ions channels are inactivated, but voltage gated potassium channels, they open. So these are voltage gated potassium channels, they open. So the potassium goes out, and these are voltage gated sodium channels. These are inactivated. So they will not be coming in or going out. Nothing would be happening. This state is known as repolarization. I will explain this in terms of graph as well later on. So, interestingly, the potassium channel has no inactivation gate. So it is either open or closed, right? So there is no inactivation gate present over here. So what happens? This is again membrane potential. So we started with minus 70 millivolt, which was the resting membrane potential. We crossed threshold, which is minus 55 millivolt, and then we reached action potential, which is the maximum value it can achieve. This was depolarization. What happens now? Repolarization is occurring, which means sodium is not coming in, but potassium is going out. So what means? That means positive is leaving. So slowly the positive will come down and we will again reach the negative state inside, because the potassium ion voltage gated potassium channels are open, so potassium is leaving, so inside becomes negative and the action potential falls. This is called as repolarization. Membrane is repolarized, coming back to the polarized state. Now since it doesn't have inactivation gate, the potassium channels are little slow to process. So what happens? They stay open for a longer time, as a result of which more potassium goes out. So potassium channels, there is no inactivation gate present. They stay open for a longer time, so more potassium goes out, as a result of which it becomes hyperpolarized. It becomes even more negative than the resting membrane potential. That is called as hyperpolarization. So at this point the membrane is hyperpolarized. What happens to the sodium channels, voltage gated sodium channels over here? During this state they would become closed. During the hyperpolarization state they would become closed. During repolarization they were inactivated, and during depolarization they were open. So that's a very important point to note over here. So, but the important thing another over here is that sodium potassium pump is working throughout. It will work throughout. It's working throughout. It will keep on working. So from resting membrane potential to threshold to action potential, then to repolarization and hyperpolarization, the sodium potassium pump would remain active throughout, and slowly positive will keep going out, and we will reach a state from repolarization to hyperpolarization. Okay, another important point is what is relative refractory period, and there is one more term which is known as absolute refractory period. So let's talk about relative refractory period first. When the membrane is hyperpolarized, which means the inside is even more negative than the resting membrane potential, we say that the membrane is in relative refractory period, which means it will take a usual then higher stimulus for it to get activated, for it to get stimulated, or for it to fire, or for it to reach action potential. It requires higher than usual stimulus for it to reach action potential. But it can be stimulated. That's why it is not absolute refractory period. At this point of time, when the membrane is hyperpolarized, you can see that the sodium channels, voltage gated sodium channels, are closed. These are voltage gated sodium channels. They are closed. And the potassium channels, voltage gated potassium channels, they are open. And as a result of which membrane is hyperpolarized because more potassium is moving out. That is known as relative refractory period. There is one more term which is known as absolute refractory period. So what happens during this? At this point, as the name suggests, absolute refractory, which means it cannot be stimulated, it cannot reach action potential. Why? Because membrane is in repolarized state. So this happens during repolarization. So during repolarization, because the voltage gated sodium channels are inactivated, they cannot open and the sodium cannot come in and it cannot be stimulated. Therefore, we say that the membrane is in absolute refractory period because it cannot fire an action potential during that time. To summarize it, we have sodium channels and we have potassium channels. Sodium channels, this means it is closed. It is closed. Sodium channels are closed over here. This means it is open, so sodium would come in. This means it is inactivated. And this means it is again closed. Right? Potassium channels closed over here. Open, which means they will go out, and closed again. So for potassium channels, we have only 3 states, and for sodium channels, we have 4 states. When the membrane is polarized. So this happens when the membrane is polarized. Voltage gated sodium channels would be closed. Voltage gated sodium potassium channels would also be closed. When the membrane is voltage gated sodium channels open and there is rapid influx of sodium ions. Then there is repolarization. What happens to the sodium channels? Voltage gated sodium channels becomes inactivated. This is during repolarization. They become inactivated, whereas the voltage gated potassium channel, they open, as a result of which potassium moves out. Then during hyperpolarization, the voltage gated sodium channels, they are closed. So this happens during hyperpolarization. And what happens to this potassium channels? They are initially open, but then as we reach the end of hyperpolarization, they would become closed. So that is what happens to the potassium channels during hyperpolarization. In terms of graph, we are assuming that the excitatory postsynaptic potential has arrived, which means it is going to be excitatory impulse. So here we have mentioned minus 65 because in some books you will see it is minus 65 millivolt, but we are referring here as minus 70 millivolt. So that is the resting membrane potential. Once it reaches the threshold potential, this is your threshold value, it will fire the impulse, it will fire the action potential, which is the 40 millivolt. Right? This is your depolarization phase. At this point, the membrane is said to be polarized. Now, this voltage gated sodium channels inactivated, voltage gated potassium channels open. That is known as repolarization. And this is your hyperpolarization, when they stay open for a long period of time, and this is again your RMP is restored. Like I mentioned, during the repolarization, membrane is said to be in absolute refractory period because the voltage gated sodium channels are inactivated, therefore the membrane cannot be stimulated and it cannot fire action potential. Whereas in hyperpolarization state, it is said to be in relative refractory period, which means it requires higher than usual stimulus for it to reach action potential. So that's all for today's lecture, and we'll come back soon with another topic. Thank you.